So yeah, apologize for the surprise talk. This was a bug filed in August this year, or September, yeah, August, which was supposed to have been patched in November, or then December, and then it became January. So I wasn't sure if I was going to be able to give this talk, but thankfully Microsoft was kind enough to let me know last night that it was okay. In their defense, I sent the slides last night, so it's what it is there. So I'm here to talk to you about breaking protected processes in Windows. If you don't know what protected processes are, it's no problem, we'll talk about what those are. And if you ever did any DOS programming back in the day, you might run protected mode and real mode and this unreal mode in between, so that's where that comes from. So, quick bio by myself. I worked on OS kernels pretty much my entire life. Started working on React OS about 10 years ago, which is an open source re-implementation of Windows NT. And after spending 10 years reverse engineering Windows, I wrote a book on Windows, Windows internals, and then I went to the most logical place ever to work, Apple. So then at Apple, I worked on the OS kernel for iOS. And basically my passion has always been working on OS kernels and finding design flaws. Bugs that are not heap overflows or stack overflows or one-byte corruptions, but bugs that are design bugs where people decided this is a good idea to do. And this talk is a very good example of that. It's not a bug per se, it's really a design flaw. Someone did not really think it through. So I'll share what I can until it gets passed in January. So, protected processes, what are they? So you're probably familiar with the idea that if you're on your computer and you're an administrator, then you can do whatever you want to your processes. You can kill them, create new ones, and you're in user mode, but you're the administrator of your computer, you have full control. That's the normal way things have always been. In Windows Vista, Microsoft came in and said, well, no, there's some processes, there's some things running on your computer that even if it's your computer, you can't really do anything about them. They're kind of black box processes. And they were invented for digital rights management. Basically, around Vista, we have Blu-ray, HD DVD, audio from the Windows Store, and the Hollywood companies did not want you to get the DRM keys and crack movies at home, since we know there's no piracy in the world because of this change. So the idea of protected processes was basically, here's a process that runs, it has access to special DRM keys, special decoding functionality, and you cannot access that process from user mode. Even if you're admin, even if you have all the rights in the world, this process is kind of more important than that. And it was truly just for DRM. In Windows 8.1, they went back and said, well, that's actually a neat technology, creating a process that's protected from everyone else. Why don't we use that as part of the security of the system? So Windows 8.1 basically takes the idea of a protected process for DRM and extends it for other things. For example, past the hash attacks. Some of you that went to the Mimikatz talk probably was mentioned how you can now configure LSASS to basically be protected against some kinds of attacks that uses protected processes. Some of the bugs inside CSRSS that were found by researchers and used to jailbreak the Windows Surface tablet. You can't do that anymore because of protected processes. So it closes down a bunch of exploits, makes dumping things out of LSASS harder, and it's generally a pretty interesting security feature of the system. The way it's all designed is based on digital signatures. So before the models were simple, something is signed or unsigned, and then you can have a policy that says if it's signed, it loads, if it's unsigned, it doesn't load. What protected processes do in Windows 8.1 is they use different kinds of signatures to decide just how trusted or how protected should this process be. So if you take, for example, a process signed by the Windows team at Microsoft versus a process signed by Microsoft, but perhaps by the Office team, or a process signed by someone but not Microsoft, or a process that's not signed at all, you can start making distinctions and differentiations between these different types of processes. So there's a whole architecture around signing levels that we're also going to talk about. And this changes a few core security paradigms of Windows. Basically now if you're admin, you don't have full control of the system. Even though you're the system account and you have all the privileges, there are some things you still can't access. So it's not true that admin access is equal to kernel access. It isn't anymore. And it also now creates these new protected processes that can have interesting behaviors. For example, I'm going to show you a demo. In Windows 8.1, you can have a process that you can't kill anymore, which is kind of strange because as an admin, you expect, hey, I should be able to kill that process. It's my machine. Well, Windows says, nope, this is a special process. You're not allowed to kill it. So we'll see some examples of that as well. So first thing we'll talk about is just a quick little brief info on code signing, kind of how that works in Windows. Then we'll talk about signature levels, because really the key security boundary here is around signatures, and if that breaks, then everything else breaks. Then we'll talk about how those signatures are used to protect processes and to protect services. We'll talk a little bit about UEFI, and the reason that's relevant is we'll talk about how LSASS is protected now. And in that section, we'll also talk about basically the bug that exists and how that can ultimately be leveraged to break protected processes. And get a tool like Mimikatz, for example, to still dump passwords on Windows 8.1 without doing what it does today, which is to load a driver. Today, the way it functions is by loading a driver, which bypasses all the security, but you need a signed driver for that. Microsoft has to approve it. It's a lengthy process. It's risky. You have to pay money. You don't have to do that with this flaw, as you're going to see. And then last thing I'll talk about is some changes in Windows 10, which make this attack and other similar attacks way harder to pull off. There's some very interesting changes that are going to happen there. So, portable executables, those are your standard Windows binaries. You can sign those through what Microsoft calls AUTHENTICODE. And AUTHENTICODE is basically based on the X509 digital certificate standard, where you have a signature that ties an application to a public key. And that public key is associated with some software publisher that obtained a certificate from someone like VeriSign or FOD or DigiCert or one of the respected, in quotes, certificate authorities. The cert then has a hash, and you compare the hash of the binary with the hash that's in the cert with the key to make sure it's the correct signed hash of that binary. And if it matches, the binary hasn't changed, it hasn't been modified, and you know that the binary basically comes from that publisher. Now, over the years, this model has been extended by saying, well, I'm Windows, I have 4,000 binaries. If I sign all of them, that's 800 or 80 megabytes worth of signatures, all saying this is a Microsoft binary. So instead you can have a catalog file, which is basically an array of hashes with a single public key. And then you can just use a catalog instead. The other problem is, well, if I have to check the hash of a binary, and the binary is 80 megabytes, then I have to hash 80 megabytes of data, which kind of goes against the idea of demand paging, right? When you double click on a process, you don't want to load all the 80 megabytes. But if you have to hash it, then you have no choice. So then you have page hashing, which says, as I load every page of the process, I'm going to have a signature for every page, and that speeds up things. But it makes for bigger signing of data. And then the stricter requirements are added. Over time, for example, we started with MD5, then some attacks proved how useless that is, then we moved on to SHA-1, and now Microsoft is forcing SHA-256 starting in 2016. So the model hasn't really changed, but it's been improved over time. Now, one of the key things about certificates that wasn't really used by Windows, but was used in other domains, is something called enhanced key usage, EKU. And the EKU of a cert tells whoever is processing a cert what this cert is used for. So you can get a certificate for your website to have SSL, so people can buy securely things on your website. Well, just because you paid $19 for your website to have a shopping cart feature doesn't mean you can use that certificate to sign a driver. And just because you signed a driver doesn't mean you can now have a shopping website with an SSL certificate. So different certificates are intended for different uses, and the EKU lets you encode what was this certificate designed to do. And what Microsoft has done in 8.1 is basically say, well, EKUs can really be any number you want. So you can actually use the EKU to encode things like this certificate is to be used for antivirus software, or this certificate is meant to be used by Microsoft software, or this certificate says that this is meant to be used for validating X. So you can really build on EKUs and encode any custom data you want. And Windows now does this as part of the model of signature levels that we're going to see. So, for example, a traditional EKU you'd see in a cert is the code signing EKU. And that's just basically this number 136, whatever it is. That just tells Windows that is a code signing cert. And then they added another EKU which says this is a Microsoft cert. In other words, Microsoft specifically issued this certificate, and that's what you can see on OS files. And then in Windows 8, they introduced something called early launch anti-malware, a special kind of driver that is designed to hunt for rootkits and viruses. Well, to be that special kind of driver, you get some special powers. To get those special powers, you have to have this EKU, this other number. And then in Windows 8.1, they added additional EKUs for the protected process stuff that we're going to talk about. So EKUs are a way to basically determine what is the exact purpose of the certificate. What does it do? What is it trying to say? It's almost like a claim. So as an example, here's the EKU for a
core Windows binary. So it'll say, for example, code signing. It'll say it's a Windows system component. So it's not just a Microsoft certificate, it's a Windows certificate. And it even is a Windows TCB component, trusted computing base. In other words, this is something for the core part of the system. And you'll see under protected process, which is what we're going to be talking about. So this, because it has this EKU, this entitlement almost, whatever binary you're looking at will be allowed to run as a protected process, and it's considered a highly trusted Windows application. We're looking here at SMSS, by the way, which is one of the binaries on Windows. So this binary is very powerful because of the certificate that it has, and we'll see how that works. And here's just the same thing on Windows 10. Basically, there's some new EKUs they've added, like lifetime signing, which means there's no revocation needed for this, and one that actually, it says unknown, so I don't know what this one is, but it's something new in Windows 10. So you can use a certificate if you're in File Explorer, basically, and look at different files on your system and see what are they meant for. So these EKUs are then used to create what are called signature levels. So in Windows 8, they added this ability to differentiate between a Windows file, a Microsoft file, and a third-party file. And the reason they added this differentiation in Windows 8 was because of the Surface tablets and Windows Phone. On Windows Phone and Surface, you cannot run applications that are not from the Windows App Store. You have to run Metro applications from the store. But on the Surface tablet, if you've ever bought a Surface RT, wrong one, so not the Surface Pro, the standard Surface or the RT, you can run desktop applications if they're Microsoft signed. So you can run Office on Surface RT, you can run Paint, Notepad, and Calc, but you can't run third-party software. That's why they had to jailbreak it. So Windows 8 now had the capability of knowing this user mode binary is Microsoft signed or it's not Microsoft signed. And that's how Office could run, but other apps couldn't. And the way this was done is by introducing some numbers in the signing system. So basically 0 is a signing level that says we haven't checked this file yet. 1 says this file is unsigned. 4 says this file is signed by someone. It's a valid, authenticated signature. 8 means it's a Microsoft signature, so for example, something like Office. And 12 means it's a Windows signature, so something like Paint or Notepad. In Windows 8.1, they then added a whole bunch of other levels for the protected process feature that I'll mention. So they had, for example, 6 for Windows Store applications, 7 for anti-malware applications, 14 for trusted computing-based applications, and you can also add custom levels as well through a signing policy. These levels are based around, first of all, who is that certificate from, what EKUs are there in it, and what OS is this and what the policy is. So for example, if something is signed by the Microsoft Corporation as the publisher, then it can possibly run as 8 or higher. And if it has an EKU saying system Windows component, then it will run at 12. So to run at 12, you have a certificate from Microsoft, and it has to have an EKU that says I'm a Windows binary. 8 just means you have a certificate from Microsoft. And 14 means you have a certificate from Microsoft, from the Windows team, with the additional EKU that says TCB. So different combinations of different EKUs and different signers combine into one of these numbers. Now, how are the numbers used? So the numbers are basically used depending if you're on a desktop system or on an RT system, so like a Windows Phone or Windows tablet, so in an embedded system. On desktop systems, they're only used for protected processes. So we'll talk about protected processes, and then we'll see how these things are actually used. On Windows RT, though, on embedded systems, these are computed anytime you launch anything. And the reason they're computed anytime is because this variable in the kernel, SIL, signing policy, is not set to 0. It's set to 0 on normal systems, which basically means run anything you want. There is no signing policy. But if this number is anything else than 0, then this says, what is the minimum signing level of any application that wants to launch? So if your signing policy is 4, that means that nothing else will launch other than signed applications. If you make it 8, then only Microsoft applications will launch. If you make it 12, then only Windows applications will launch. So process launch is gated on what your signing policy is and what the signature of this file is. That's called the executable signing level. But on top of that, any DLL that application loads, well, if you can load any arbitrary DLL, then that DLL can run in the context of the process and attack the process. So each application also has a DLL signing level, which says what is the signing level, the minimum signing level of any library that's going to load inside this process. And that way, for example, you can have a level 12 application, which is a Windows app, But it might say, I'm okay with loading Microsoft DLLs. So I don't want to load only Windows DLLs, I also want to load an Office DLL, for example. So there's a DLL signing level, and there's an executable signing level. And the system determines what protections are applied for which, and I'll show you a few examples of that. So let me show you what it's going to look like if I actually change. So right now I'm in a normal system, so I can pretty much run any binary I want. Like on my desktop I have PuTTY, which I don't think is signed. Yeah, it's not signed, so if I run PuTTY, no surprise there, it runs. So let's change the signing policy. So change the signing policy to 4, which means AUTHENTICODE signed. So now I'm baking the fact that I have a signing policy of 4. Now if I try to launch PuTTY, it says Windows cannot verify the digital signature of this file. It will no longer let me launch because PuTTY isn't signed. But if I launch any other signed application, like I believe IDA is signed. Oh, it's not. Well, VirtualBox is signed. Or both those there. So VirtualBox still launches fine because the executable is signed by some valid cert. So now if I set the level to 8 though, 8 remember means Microsoft. Now if I try to launch Oracle, it won't launch because Sun, thankfully, is not the same company as Microsoft. Now can I launch DBGView, which is a sysinternals tool? I can still launch sysinternals because sysinternals got acquired by Microsoft and sysinternals tools are now signed by Microsoft. So that works fine. And as a final test, let's say I put it up to C or 12 and decimal, meaning Windows binaries only. Now if I try to launch DBGView, I get an error as well. Because now I literally can only run Windows core binaries, like I can try running calc, for example. That's going to work just fine. So that's one part of the system if you're on an embedded machine, like on Windows tablet or Surface. But on a desktop, you're usually at 0, so you can run anything you want. So these are then used by protected processes instead. On desktop, you normally don't have that feature enabled. But it does exist in the kernel, and that's how they protect unsigned applications from launching on other systems. Now, all of this information, like what makes my system, how come I can launch anything I want on my machine, but you can't do it on a Surface tablet? It's not that the kernel knows, oh, this is a Surface tablet, or this is a phone. It's in secure boot infrastructure, which is used on EFI systems. There's something called the secure boot policy. And the secure boot policy basically tells Windows on an EFI machine what signing level policy should be enabled. 0, for example, on x86 and x64, 8 on ARM, and a few other additional settings. For example, a secure boot policy can say you're not allowed to turn debuggy mode on. So those of you that have laptops in secure boot, if you ever turn debuggy mode on, it tells you I can't do that. The reason you cannot turn debuggy mode on a secure boot machine is because your secure boot policy doesn't let you do that. Test signing mode also can't be enabled. So this is basically a binary file that instructs Windows on what the policy is, what should be allowed to run, all the way from boot to kernel mode drivers to user mode applications. And this is either going to be loaded from a signed file, which you probably won't find on your machine. But you might, for example, buy a laptop from a vendor that has a secure boot policy on your laptop that might say, this laptop can only boot applications from Intel. And now it's going to have the Intel cert in the store. It's going to say only Intel apps can run. Which is kind of stupid because then you won't be able to run anything, but you could do that, for example. If the file isn't found, it's going to be the variable called current policy. So your BIOS manufacturer or EFI manufacturer could have also put the signing policy in the file, and if you do, in the variable. And if you don't have a variable and you don't have a file, the last thing it's going to do is going to read the policy in the boot manager itself. So the boot manager file has the default signing policy for your machine. And bootmgfw is the default one on Windows x64 and x86. And then there's bootmgfw ARM, which is the ARM one. And the ARM boot manager has a different default setting. Now, can you go on an ARM machine and change this to 0 or mess with this? No, because the signing policy itself has to be signed. And it has to be signed by Microsoft or by your vendor, by whoever has the platform key. So the system is pretty much starts secure from the start. Okay, so we have these levels, these numbers that tell us what's signed. What does Windows use them for other than blocking application launch? It uses them for data of a protected process, which I mentioned was originally introduced in Vista to prevent you from cracking digital rights management applications. So if you're playing a DVD movie and it was getting the keys from the kernel, obviously the keys are in user mode, you could use a debugger attached to the process, and then you get the keys out of there. So with the protected process, you create this process with a special flag when you call create process called create protected process. This checks if you have a special Windows Media DRM certificate, and if you do, it sets a bit in the kernel structure that says this is protected. And then there's some drivers in a system that basically manage access to the DRM keys, and they make sure that only protected processes can get the keys. So there's an undocumented control code that you can ask Windows, give me the symmetric key to decrypt movies, and it'll only give it to you if you're protected. And for you to be protected, you should have been signed by the Windows DRM team at Microsoft. And because you're protected, what can happen to you? Well, other processes of the machine can only kill you, they can suspend you, they can wait on you, or they can ask things about you. But they cannot modify your memory, read your memory, inject threads into you, create processes under you, inherit handles, duplicate handles, access your token. Basically, the only thing you can do to this process is kind of kill it, look at it in Task Manager, and wait on it to die. So protected processes can do anything they want to other protected processes, but non-protected processes can't do anything. Debug privilege doesn't change a thing. TCP privilege doesn't change a thing. System account doesn't matter. You cannot touch these guys unless you go to the kernel. So in Vista, you had the protected media path executable, which is video, and audio DG, which is audio. And these two binaries are protected in Vista and later, and they still are protected today. So if you try attaching a debugger to one of these, you'll see that you're not going to be able to do that. So in Windows 8, small change is that instead of having a protected process bit, the signature level now encodes, since we added signature levels for ARM, we OR bit number 1. So if you look at the signature level of audio DG, its signature level is normally 4. 4 means anything that's signed, because audio DG can load third-party signed applications. And so because of that, audio DG is running at 4, but because it's protected, you OR in 1, it runs at 5. On Windows RT, though, where only Microsoft signed things can load, audio DG is going to be 8, which means Microsoft, and then we OR 1, because it's protected, becomes 9. So really nothing has changed other than some internal details of how that protection is implemented. It's still a DRM feature. The one thing that does matter, though, is because the system process is also protected, there's a bunch of stuff in the user mode memory of the system process that happens now. So there's certificate decoding that happens, there's driver loading that happens in the user mode region of the system process, which you could normally access as an admin. But because the system process is also protected, there's some attacks that you could do in XP, for example, that you can no longer do because of that. So it was a DRM feature, but it also did have some benefits for the system. But that was about it. So what happens in Windows 8.1, you now have a new distinction. You have multiple signers. So something is not just protected or not protected, but it's protected by someone. It's protected for some reason. And you have different protection types. We're going to see what those are. So the signers basically tell you, they're kind of similar to this, they're related in a way to signature levels. Basically says the signer can be an AUTHENTICODE signer. So this is a protected app that is just signed by someone. CodeGen means it's signed by .NET. Anti-malware means it's for Windows Defender, another anti-malware tool. LSASS is used for pass-the-hash protection that I'll talk about. Windows, meaning it's signed by the Windows team. And Windows TCB, meaning it's a core component, trusted computing-based component of Windows. So these are different levels at which a process can be signed. And then the different types of protection are the normal one, which is the one from Vista. And then they added a light protection. So you combine these two numbers together, and the top nibble is the signer, and the bottom nibble is the type. So 31 basically means it's an anti-malware, because that comes from this number here, and 1 meaning it's light, because it's 1. So this is a lightly protected anti-malware process, would be 0x31. What that basically means is you now have a hierarchy. Basically tells you protected processes can touch any other process they want, as long as they are at or below this level. So something that is 52, for example, means that it's Windows and protected. So we can go harass 51 if it wants to. We can go harass 42, 31, basically any levels below and any protection levels below, but it cannot touch 62 because 62 is TCB protected. The signer is not powerful enough. Or it's another example, if you have something at 31, well, 31 cannot access protected processes because that's full protection, which is 2. It cannot access 41 or 51 because that number is higher. So 31 can only access other 31s, 21s, or 11s. So protected processes are more powerful than light processes, and then within your protection level, the signer determines what you can do. And the idea here is, for example, if you protect LSAS against password dumping, well, anti-malware apps, even though they can run protected, even though Symantec can run protected, Symantec won't be able to attack LSAS either. But LSAS can attack Symantec if it wants to. That sounds kind of weird. So when are these used? Well, they're used for different features. So for example, LSAS process is not protected against memory reads and memory writes. Anti-malware processes are protecting against memory reads and memory writes and also against termination. And so are TCB processes. So now you have processes that can't be killed anymore, which removes what used to be a hack called critical processes. Also now, because more processes are critical than just DRM processes, CSRSS, for example, is critical, is protected. Now CSRSS had an exploit in it, a bug, which was published online about 4 years ago, never fixed by Microsoft, and then used 2 years ago by the Surface jailbreak team to basically attack the kernel on Windows 8 on the Surface and turn off the protection. And they're able to do that because it was a known, not a 0 day, but a two-year day. And all it required is injecting into CSRSS and then attacking the kernel. Well, now you cannot inject in CSRSS anymore because it's protected, and so the exploit basically dies. Because the only way for you to actually inject in CSRSS is to be protected yourself, which means you have a signature from Microsoft, which is obviously not going to happen. It makes dumping stuff in LSAS harder, and it makes it harder to get a system token as well. Since the core system processes now have protection on, you cannot just steal a token from those processes. You're going to have to go after another process. So how do you create a protected process? Again, you still use create protected process when you call create process, but then you need to specify the actual level. So there's a new protection level attribute that you can add, and basically this says, how do you want this process to be protected? Do you want it to be protected? So Windows app, full protection, Windows app, light protection, anti-malware app, light protection, and so on and so forth. And then if you request protection, we're going to check the signature level of the application. In other words, if something does not have an EKU saying it should run protected, it can't run protected. And if you're claiming this thing should run as a Windows protected application, if it doesn't have a Windows certificate, it's not going to be able to run with that. So this forces the signing levels check to happen to actually make sure you're allowed to get that signature level. Which means that for something to launch protected, someone has to request it to launch that way. So the system process launches SMSS as 61. Basically, Windows Core Component TCB Protected Light. SMSS starts CSRSS at the same protection level. SMSS then launches WinInit and WinLogon with no protection, except in Windows 10, where WinInit is now also protected 0x61. WinInit then launches LSAS with 41, if you've configured this, and then it launches the Service Control Manager with 61. So then all the core system processes, they request to be launched with protection. So what about Windows Defender? What about anti-malware and those type of things? Well, those are protected services, which we'll talk about in a second. But I want to just show you that, what this means. So say SMSS is protected, for example. So if I try to go in Task Manager or any other tool and go down to SMSS and try to kill it, it says access is denied. And I am running this admin. I can even run a system if you'd like. It doesn't matter what my privileges are. I just cannot kill SMSS anymore. Or MSNPENG, which is the Windows Defender, the Windows antivirus. If I try to kill this, it just doesn't let me. And it doesn't let me because it's protected. If I took off the protection, it would work just fine. Another example, let's say I want to take a dump of CSRSS. So create a dump file for it, also not allowed. If I try to attach with it from the debugger, so let's launch WinBag, as administrator, full debug privileges. Normally this can attach to anything you want it to attach to, but if I try to attach to SMSS, access is denied. So this is the protection level in place. Now all it would take for me is to go in the debugger now and change the protection level of SMSS, and now I could attach it to the debugger if I wanted to. Or I could change the protection level of WinBag, lie and say that's protected by Microsoft, and now I could also attach. So of course with the kernel debugger connection, you can break this, right? This is designed to prevent admins from doing things. But if you can load a driver, then you're home free. But to load a driver, it has to be signed, and on systems with secure boot, it has to be SHA-256 signed, and on systems like the Surface, for example, it has to be Microsoft signed. So on a Surface or on a Windows Phone, you have to load a Microsoft signed driver to break protection. Well, then you're not really breaking anything because it's a Microsoft signed driver. So you have to find a bug in a Microsoft signed driver, use that. So it's a pretty strong model. So from WinBag, you can see that something is protected, because obviously you can see it because I'm just trying to kill random things. But there's actually a flag in the eProcess structure that tells you if something is protected or not. So if you take a process, like let's say SMSS, so that's dumping a little bit too much there. 0. So none of the debugger commands, none of the tools that should by default tell you something's protected, but if you look into its structure, if you're familiar with eProcess, there's something called protection. And the protection level is basically what we've been talking about so far. So 61 in this case for, I think this was SMSS, basically meaning Windows TCB and protected light. If it changes to something else, then it's going to lose that protection. It's not going to be protected anymore. And if I modify something to be protected, then it's going to do the exact same thing. So I'll show another script after so you can see that. So what about things like anti-malware or other third-party things? So those are called protected services. So when the Service Control Manager launches a service, you can also ask for it to be protected. And there's a whole new documented way of doing this, because Microsoft has actually documented this because they want third-party service providers, if they're anti-malware developers, to implement protection in them as well. So you can check with the Service Control Manager if something is protected. There's a new SCQ protection query, and if I check, for example, the Windows Software Licensing Service, which protects Windows against piracy, it says this is protected Windows. So this is a Windows protected process. If I then check, let's say, Windows Defender, Windows Defender is anti-malware light. So that's a different level. And this will match what you would see in a debugger. So SVP, SVC, because it doesn't say light, will be type 2, meaning full, and Windows 5, so it'll be 52. And this one will be 31, because it's anti-malware 3 and it's light 1. Now, that's why these other processes are also protected. So if I try to go to WinDefend, like I just showed you, MSMP, ENG, I can't kill it. Now, why don't I just stop it or uninstall it with Service Control Manager? Because this will send a command to the Service Control Manager. The Service Control Manager is running protected. It's running at 61. It should be able to kill Windows Defender. It can't. But it's smart enough to check who is asking you to do that. And if SC, or whatever you use, the API to ask it to stop Defender is not protected, then it doesn't matter that it is protected, it just won't kill it for you. So if I try to stop Windows Defender, access is denied. So it also is smart enough to prevent you from killing a process using the Service Control Manager, which normally would be able to do that. So that's how protected services work. And then once you have a protected service, you can launch protected applications. So Windows Defender can now launch other applications that are part of the Windows Defender suite and protect them as anti-malware as well. So there's always the idea that you launch something and you request a level at launch time. So that was just the thing I showed you. So LSASS is one other application of this idea. And this is where it becomes interesting to be able to dump things. So quickly, in the EFI world, there's variables that you can set. So these are like BIOS variables. Now the BIOS variables can be boot variables, or runtime variables, or authenticated variables. This just tells you, can you access them at boot? Can you access them at runtime, or do they have to be signed? They can be read-only, read-write, etc. And they have a GUID. They have a namespace that they live in. What Windows does is it gives you APIs to set runtime EFI variables, and it uses its own vendor GUID, which is this GUID right here, called the Secure Boot Policy GUID. Any variable that starts with kernel underscore goes inside of this GUID and cannot be set from user mode. So you can have basically EFI variables in Windows that are not accessible from user mode, even though there is a user mode API to set the variables. Okay, so why are these kernel UEFI variables important? Because of LSASS pass the hash protection. So in Windows 8.1, you can configure LSASS to run protected. It normally does not run protected because there's third-party LSASS plugins, like Mimikatz, or more interesting and useful for admins, third-party plugins, which are not signed. So by default, they don't do this because they're going to break every single plugin provider out there. But if you go in your registry, you can go in System, Current Control Set, Control LSA, and you can make it protected. Once you do that, something interesting happens. In a special UEFI variable called kernel LSA PPL config, Microsoft will write down the value it puts in the registry key. And then every single time you reboot the system, Windows is going to check this variable. And so even if you delete it from the registry, it's still going to be set in EFI. And you cannot touch it in EFI because it starts with kernel underscore, so only someone in the kernel can do this. In other words, once you've turned this feature on, you can't turn it off anymore. And once it's on, LSASS will run protected at level 41. So now you can't kill LSASS anymore, and so you can still kill LSASS, you can't do anything but kill it otherwise. So what if you do want to turn it off? Well, Microsoft gives you this obscure page where it tells you to download a special EFI file from them and basically reconfigure your machine using these complicated steps to basically boot into it's almost like a boot kit. It forces you to launch a special EFI app that's signed by Microsoft. And then when you launch this app, after you reboot, basically gives you a black screen and tells you, are you sure you want to do this? And I have a little video, I'll skip it. Basically, you interactively, physically have to reboot the machine, press a bunch of keys, and then that's how it deletes that variable and turns it off. So it's actually a pretty strong protection. And because of that, Mimikatz in Windows 8.1 or any other password dumping tool that works that way has to load a driver, turn the bit off, and mess with the system that way. So I thought, is there another way around this? So when Windows crashes, it takes a crash dump if you're in the kernel, or a mini dump, or a process dump if you're in user mode. And so I remember reading my own book at some point, and helps. Remembering this sentence, the audio device graph process, AudioDG, is a protected process because protected music content can be decoded through it. Similarly, the Windows error reporting client process can also run protected because it needs to have access to protected processes in case one of them crashes. Like, can also run protected? How can I get the Windows error reporting service to run protected? Because if it runs protected, then it can dump anything that's protected. It can get a dump of anything that I need. So it turns out that, yes, if a protected process crashes, it launches a special version of Warfault. That special version of Warfault, which is a process that takes a dump, has the EKU to run all the way up to 62. Therefore, it can dump any protected process that it wants. It can open handle CSRS, SMSS, and LSASS as well. And then it calls mini dump write dump. So play around with this. Okay, let me just try to get this to work. Can I get a protected process to crash? So I set up, I won't do it now, but I basically played around this, and I got AudioDG to crash. But the dumps that I had here were basically kind of useless dumps that only had the thread information. There was no memory in these dumps, so you can imagine, or you can't see the size here, but they're 400 kilobytes. So they're basically just mini dumps of the crash. I wanted to have the triage dump and a full dump. So what turned out to be true is that I did get a full dump, 50 megabytes, all of LSS's memory, but this is the actual name from Warfault, memory.protected. And if I open this up in the hex editor, very quickly you'll see if you're familiar with the dump format, but even if you're not familiar with the dump format, this is usually a bad sign, right? This is an encrypted dump. So I'm like, okay, so it takes an encrypted dump. So that was kind of interesting. So I was like, started thinking, but how does it? Because I know Windows can't internally take an encrypted dump. So how does that work? So I ended up running process monitor from sysinternals to actually see what was going on when AUTHENTICODE was crashing. And I saved a log here to show you how that looks like. I think that's the right log. I'm still loading. And the nice thing is here is that I was actually able to see the reads and the writes. Here are the, I think I skipped them. Yeah, here's, for example, the reads. That's actually hex edit, not what I want. Word fault. So here's this word fault secure.exe. And at some point, it starts reading and writing into the dump files. So let's see if I can go down. Yeah, so there's UDF and EDF, so it writes. And then I looked at a stack, and I saw this, mini dump callback. And it turned out that the UDF was unencrypted dump file. And at some point after writing the unencrypted dump file, it starts writing EDF, encrypted dump file. So you're starting to get the idea. And then on the stack, it's not visible on this one, but write file. There was the event that actually creates the encrypted dump file ended up coming from a DLL called, which got loaded. Let's see if we can find it here. There. Word fault secure also ends up creating encdump.dll, which was an initialized dump encryptor, which is loaded through load library. So all these things kind of pointed me to the way that, okay, so there is a way to get a decrypted dump, and the encryption is done separately by a separate DLL that's dynamically loaded. So you can imagine a whole number of possibilities here to mess with the system. So I'll skip the demo, just to saw those dump files. But basically it turns out that WR has this nice command line parameters that you can use. Ask it for a secure dump, ask it for the PID you want to dump, the thread specifically you want to dump in there, what kind of dump you want, what file handle it should dump the unencrypted version into, where it should dump the encrypted version into, and you can have two separate handles for this and an event so you can cancel things as well. So then I ended up creating a little tool that basically just calls word fault with the right parameters, saying, you know what, I want to dump LSASS. So I don't actually have to crash LSASS. I can just launch it, telling it to launch, to pretend that LSASS crashes. So let's go see users, Ionescu, Visual Documents, Visual Studio 14, projects, dumper, very original name. So PPL, debug, dumper. So can't release this right now, but if I just tell dumper to dump lsas.exe and tell it to dump it into, let's say, lsa.dump, and then you can give it a bunch of flags, so I will mention those, and I tell it to run dump complete. There's a little bug there, it says 0 bytes, but that's not straight true. And I just got a 33 megabyte dump of LSASS, which if I open this and the hex editor, that was an early one, open the hex edit, this is in fact not encrypted at all. It's the standard mini-dump format. So now that you have standard mini-dump format, I can just open this inside Mimikatz, for example. Let's copy the dump, lsa.dump, desktop, Mimikatz, where did it go? x64, copy it over here, run Mimikatz, and tell it secure LSA mini dump lsa.dump, and it opens it just fine, and now I can tell it secure LSA logon passwords. I forgot to change my passwords. If I do this, it'll actually dump my password, so I'll just quickly minimize and hope no one sees the live stream quickly enough. There, it got my password, trust me. It's there. So basically, with that tool, this bug, all that protection basically goes away pretty much immediately. So that's supposed to be fixed in January, so that's why I can't kind of talk more about it. But basically, a pretty big flaw, which basically undermines the whole idea. Fake that a process is crashed, and you can dump its memory even though it's running as protected. So you can actually do a little bit more than just dumps with word fault. It opens a bunch of handles. So the fact that you can actually launch the word fault application without being protected and then doing things to it can actually lead to more interesting attacks as well. So the idea is if an admin still has the power to influence the environment and to get a protected application to do certain things that it shouldn't do, you can still kind of break through the protection. And this is an example of a read type of attack. Another write attack I published at Syscan in April this year, which was using ALPC to inject memory into any process that had an RPC service. So if you have an RPC protected process, you could, using that vulnerability, which got patched in October, write anything you want in it. So at the end of the day, the protection inside a protected process still relies on the process not doing stupid things, like opening endpoints to random things, and still relies on not having a backdoor that lets you dump the process whenever you want. Now, Windows 10 is actually going to change a lot about this, other than fixing this bug. When I was doing the research, I read about something called, on the Windows blog, that in Windows 10, LSASS will run under secure container protected by Hyper-V. And then I found this binary called LSA-ISO.exe, the isolated LSASS process. And inside of it, it says that it runs a VSM-ified, virtual secure machine. Then you find things on Microsoft Research about Hyper-V secure containers. And the Windows 10 kernel has references to a secure process. There's a new attribute to launch a process secure, and there's a new check, is secure process. So it looks like we're moving beyond protected processes to secure processes, and according to that log, and according to the strings, that means that these processes will now run essentially in a VM. So this LSA ISO right now is very much a stub, but in the future it'll probably run its own Hyper-V container. Meaning that even if you're in user mode, even if you're in kernel mode, you won't be able to attack LSASS anymore because it'll essentially be running in a separate, complete enclave that has its own virtualization layer around it. So that's pretty exciting. We'll see how well that works. Obviously, this means if there's vulnerabilities in Hyper-V, you can use them. But we're moving more and more to a process where you can now have, to a system where you have processes on your machine that are actually now running their own little isolated VM. So that's a pretty exciting change, I think. So just in conclusion, protected processes are a new thing in Windows 8.1 when applied to things like LSASS, SMSS, and CSRSS. They let you have unkillable malware, anti-malware. They prevent exploiting SM binaries. They protect LSASS. But they don't protect any external attackers. And because of this little backdoor that lets you dump any process you want, you can still dump their memory until this gets fixed. And in the Windows 10, they're adding something beyond just protected processes, which are these secure processes, which will basically mean that minus a bug in a VM, they should essentially be unattackable if they do a good job with a virtualization solution. So, any questions? I'm just about done and out of time.
Thank you.
Hello. Really interesting talk. So I was expecting, I didn't know about all of those things about processes and signing and everything. I was actually expecting a short discussion about a different aspect, such that what happens if an attacker or a group of attackers actually manage to get their hands on the Windows signings certificate, and please don't say this can't happen.
So if you get access to the Windows signing certificate,
How do you protect against this one if they get their hands?
you can't. I mean, this relies on certificates being secure, and if you can create a collision against the cert or steal the cert, then this will fail, EF5 protection will fail, Windows Update will fail. I mean, I will run away and hide in a cave if that ever happens. because basically, even Linux will fail because Linux now trusts Microsoft certs as well. So that is kind of a doomsday scenario.
So, are you saying that on Windows 10, the secure processes are going to be protected even from the kernel itself?
That's what the blog suggests, and that's what the virtualization solutions. So right now, there's no real code that's been shipped yet. I mean, they're just starting on this, and there's that blog post. But the idea is, and from what I've heard, is that basically, yes, they'll be running in basically a ring level kind of beyond ring 0 in their own VM, just like if you had a Hyper-V running on a different partition, basically. So yes, even the kernel attacker won't be able to get into that. Now, on the other hand, the kernel attacker could probably attack the Hyper-V engine itself, and from then maybe do an attack that way. So I'm not going to say impossible, but it's designed to prevent against someone just reading the memory, for example.
Thanks.
That raises another question about the LSAS process. We call NT create file and stuff, which are kernel functions. So, I mean, you could still hijack the process.
I think so. The idea is that you're not going to take a whole process and run it in the VM, but part of, for example, LSA ISO has the RPC functions to get the Kerberos keys and then the tickets and all that. That functionality is running in a micro VM, basically. And it'll probably be doing hyper calls. I mean, they still have yet to build any of this in real time. So we'll see if it even ships. I mean, right now it's a blog post and a tiny, if you have Windows 10, you can look at LSA ISO. It's like a tiny 10 kilobyte binary that doesn't do much today. But that's what they're promising, at least. It'll be interesting to see how that works. Any other questions?
Yeah, I have another question about the demo, because it seems that the CMD was elevated. Can you dump any process from non-elevated command line?
No, so there's still, Warefault doesn't let you bypass the Apple protection. So if you're trying to attack a non-admin protected process, you can. If it's an admin protected process, you also have to be admin. So you still have to be at the normal privilege level that you would normally be at, but on top of that, you can break through the protected process. So it's not a vulnerability security layer, it's a vulnerability process protected layer. Because otherwise, things would be really bad if you can just launch Warefault and dump anything you want.
Other questions? We're still waiting for the draw. We still need to find a winner for the first prize because the guy was from the organization. So we still have time for one or two questions if you want. Okay, no more questions. So please stay around and thanks again our speaker for this exclusive talk.